So a database is taking a lot of unstructured data, just data that's not organized, and then organizing it in a particular way, and that's what the data structure is. After which, when you have your data organized in this way, you can do operations efficiently on it. Mainly that's insertion, deletion, search is a big one, and maybe modification. Okay, so that's where we're at, and I'm talking about binary trees not because they're used in databases, but because they're the simplest kind of tree, and what we'll really be talking about is the B plus tree. But we won't actually get into so many of the details about B plus trees. I'll just sort of say how they're different and show some operations with them. But you should have an understanding of what trees are and how they work. So that's where we'll be picking up from today. Let's go down here. Great. Okay. Before I continue lecture, I want to pause and see if there's any questions about anything. Anything we went over before. I don't know, anything. I'll take that as a no. Okay. Yeah. So let me go over binary trees again very quickly. So a binary tree is a tree that can have at most 2 children. It can have 0 or it can have 1. That's okay too. But it's at most 2 children. And the reason why it's at most 2 children is because for any node in the tree, let's see if I can highlight this. For any node in the tree, these are, a tree can, you can always answer the question, is something bigger than or less than equal to? The equal to, it doesn't matter which side you put it on. Just be consistent. So for some value that would go here, this value must be greater than its parent. Similarly, any values on the left must be less than or equal to the parent. Okay, so this is an example of a binary tree, this really long chain. And it's a valid tree, but it's not a very useful tree. It works more like when you have a tree like this, where there's just a big long chain. It doesn't have the best properties to it. Where we would prefer trees to be balanced. And what a balanced tree is it's a tree that there's a few ways you can phrase this. It is as shallow as possible. The depth of the tree is as small as possible. All of the layers from the root down to the leaves are full, meaning every single point is occupied, except maybe the last layer. The last layer doesn't have to be full, but every layer above that is full, okay? So this tree here on the right, this is balanced, but it's not full. The first layer is full, the second layer is full, but the third layer is not full. So this counts as being a balanced tree. For the purposes of, and this is what we care about, okay? We just want things to be balanced because things can't always be full. For example, here, if you only have 5 numbers, you can't make a full tree. There's just, you don't have enough values to occupy the spaces. But for the purposes of this lecture, we're going to be focusing on full trees, just because the nice properties of it are a little more apparent. Okay. Now, the reason why this is also called a binary search tree is because it's amenable to doing a binary search. Because all of the values to the left of any node are smaller, and all the values are less than equal to, and all the values to the right are greater than, then you can start at the root, and assuming that, there's numbers everywhere, which I didn't fill out here, but you start at the root always, and then you what's called traverse the tree. Okay, so traversing the tree means you start at the root, and maybe we're looking for the number, I don't know, some number that's going to be here. Okay, that's where we'll end up. So we start at the root, and whatever number that is, it's going to be less than the number 20. So you can branch left in the tree, and now you're looking at the value 10. And the value that we're looking for is bigger than 10, so we can branch right. The number will be smaller than whatever is here. You branch left, and now you find the number. Okay, so that is going to be how a binary search is conducted on a binary tree. Now, you'll notice that the longest path that you will have to take in the worst case is going from the root all the way down to the leaves. Okay, that's the reason why we want the tree to be shallow. We don't want a deep tree because we want every search to be fast, no matter what number we're looking for. And so the best way you can do that in this tree is to have it be balanced. Okay, if we go up here and look at this, again, it's a valid binary tree, but why would this be bad for a binary search? Well, let's say we're looking for the number 1 billion. That's the worst case scenario. You would start at the root, you'd go right, 1 billion's bigger than 12, 1 billion's bigger than 13, it's bigger than 14, it's bigger than 15, it's bigger than 16, and on and on and on until you finally find it. But that is basically doing a linear search, right? I mean, you're visiting everything that exists, and so that wastes time. If you have a tree that's not balanced, then the binary search doesn't have this log n time guarantee, because there's no way to jump around the tree. You can only start at the root and step by step traverse it, going deeper and deeper each time. Okay, so that's why we care about having balanced trees, because now no matter what number you're looking for, the longest path that you'll need to take is from the root to the leaves, and the depth of this tree is log n, where n is the number of nodes. So in this tree, there's 31 nodes. Log base 2 of 31 is 5, close enough to it. You would just round here. And that's it. So at most, it will take 5 steps to find any number here. Okay. So if you have n nodes, then there are log n layers. And because any path that you take at most is going to start at the root and go down to, to some leaf node, and the longest path is log n, then this search algorithm will only take log n time. Okay. Let me pause and see if there's any questions about that. Nothing. Well, it's a very silent class. Okay. Right. Let me... First, I'll ask just the class. Hopefully somebody answers. Or even saying, I don't know, is a valid answer. Okay. Why, if you can do a binary search on an array, why are we talking about a tree? Like, what might be the benefit of using a tree to do a binary search instead of an array?
It might be a little bit faster. And it has a little more structure to it.
Say that again?
It's probably a little bit faster, and it probably has a little more, well, not probably, it has a little more structure to it than an array does.
It has more structure to it. Okay. Great. Everything is already sorted. Okay. More organized. Don't need to sort. Easier to visualize, that much I think is true. I mean, I kind of maybe went too deep last time. You don't need to remember all that stuff as far as like encoding things in binary and all of this, but there's a lot of very cool things that happen with the binary tree. It's easier to add and delete from a tree rather than an array. That's probably the closest to it. Arun, can you speak more about that? Why do you think it would be easier to add and delete in a tree instead of an array?
Mostly because, like, in a tree, you can add an element to the tree, but when you add something to an array, you have to make an entirely new array. So that takes more time with more elements.
Yeah, very good. Yeah, that's basically it. So I'll repeat that. And now we're going to be delving a little bit into actual hardware for this. And we'll come up with we'll come to sort of a contradiction. And we'll see if there's anybody who can think of how to get around it. Okay, so that answer is basically correct. When you have an array and you want to add a new element, you might need to just create a new array. Let's see, I see another answer. The longest path of a tree depends on the number of layers. That's true. But keep in mind, if you have a sorted array, right, it also takes log n time. So, by the way, maybe I'll come back to that. Or, I don't know, whatever, if we have time. It's just a practice question. Okay. I don't know, let's do... So here's a binary tree. and it will take at most 3 steps to search. At the same time, you can have an array like this, and well, you just have to put the sorted numbers: 4, 5, 7, 15, 20. Oh, sorry, I forgot the 10. 7, 10, 15, 20, 30. Okay, so we could also have an array, and you keep it in sorted order. Each of these will have a search time of log n. So, right. Okay. Now, for the tree, let's say I wanted to add the number 1. Okay? Then for the tree, everything always starts at the root, so it's similar to a search, except you're just searching for where it should be inserted. So here, you start at 10, 1 is less than 10, so you go left, 1 is less than 5, so you go left, 1 is less than 4, there's an empty place there, so you can put 1. All right. Now, in the array, so that is to say, for the tree, let me write this here. I'll move this over a bit. So array and tree. Each of these you can search in time log n. Okay, already talked about it for the tree. For the array, when it's ordered like this, you break it in half, break it in half, break it in half until you can only do that log n times. So search log n. Now, insertion in the tree also takes time log n. As I just did. I mean, I had to put it in the leaf, and so that's, you go down the depth of the tree is balanced, so it's log n. Here, you don't need to know how to maintain a balanced tree, okay? That's for like a data structures course, okay? Just know that there's a preference, a strong preference, to have a balanced tree. And there's algorithms where you can insert and delete, and it will maintain this property, that the tree is balanced. You could look at like a red-black tree, for example, if you're interested in that. But that's not this course. Okay, but now for the array. How do we insert element 1? Well, there's no room, so we have to create room. So we can add a block here, right? But 1 doesn't go at the end. So we have to delete 30 and move 30 here, and then delete 20 and move 20 there, and then delete 15 and then move it. And, we have to shift all of these things down. And now we have room to put the 1. Okay, so here, using an array, insertion is time n. This, I have to tell you up front, I'm kind of lying to you. This actually isn't the case. You can do better than n, but when the array is sorted in this way, it would take time n to insert, also delete, okay? Deletion for the same reason would take time n. Like if I wanted to delete the number 1 now that I've inserted it. Well, I have to delete it. I can find it quickly, log n, but then once I delete it, then I have to shift everything back. And yeah, you can't have empty spaces in an array. And I won't go through how, but you can just trust me that this also takes time log n on a balanced binary tree. Okay. All right. Why can't you add space at the beginning of the array? You can only do it at the end of the array. This has some technical reasons for it. Basically, when... Let's get into hardware. Nothing will make sense, or things will make more sense if I talk a little bit about hardware. Okay. Before I do that, though, any questions about this? The array versus the tree. The search is fine, but the insertion and deletion sucks. So for that reason, we prefer the tree. No questions. Okay. Then, let me do this. Okay. So I need to find everything right here. What? Oh, I'm missing that. Oh, okay. Okay. Well, fine. This is. Oh, good. Here it is. All right. So, how are things stored in a computer? This is a hard drive. Okay, this is a disk drive. So inside of this is it's actually a series of disks. I'll draw a quick picture. So inside of this, and I would open it up, but when you do that, like even if dust can get in, it can like destroy a hard drive. And I don't have any dead hard drives, so whatever. So there's a series of disks like this inside of this drive. Okay. All of these spin. Okay, like if you've ever booted up a hard drive like this, you can hear it spinning up. You know, you can hear it starting to whir. If you hold it while it's on and move it around, it's like a gyroscope because things are spinning inside of it. And so, you know, like riding a bike or whatever, it wants to maintain its position. So whenever you move it well, two axes, then you'll get some pushback. All right, so these are disks. And then there's a head. This here. And there's actually a head on each one of these. So this is a head. Okay, all of these are heads. Okay. And the head works like a record player. If you've ever seen how those play, where you have a needle and the record spins and then the needle sits on top of it. And for a record player, it's actually little grooves that are inside of the record that the needle actually like touches and goes up and down, and that makes sound and whatever. But the mechanism is similar. Okay, so these disks spin, and then this head, you can move it. So this head can move around, same way like a record player's needle can move, except for the needle you have to pick it up on a record player, but this has like a motor here that can move the heads. So this way you can read any part. Let's see. Oh, like a record as well, here, you have tracks. Let me see. This is a track. Tracks. Okay. So just like a record player, or like a record, if you've listened to or looked at a record, you know, there's different songs, and if you want to play a particular song, you have to pick up the needle and place it down on wherever that track is. If you start on, I think, yeah, usually you put the pin on the outside, or the needle on the outside of the record, and then it'll slowly kind of make its way towards the center, and then that will play whatever side of the album that is. Fine. So just like that, there are tracks on these discs. Also, there are sectors. It's like if you cut this into a pie, a sector. Okay? So all of these are sectors, like slices of a pizza. Okay? And right. So any location on the disk will be like this. This is both, here, let me do it this way. If we have like a track here, and then we have a sector here. All right. Then this, the intersection of the two, that is a block. Okay, that's the smallest unit in a hard drive. A typical size is maybe 512 bytes. Okay, like a half a megabyte. Okay, so that's how these work. Okay, and fine. So, and this is typically what databases are going to use. We'll talk more about why that is. But if you've never seen a hard drive, this is one. This one is 8 terabytes. Okay, so a decently sized disk. And this is also used for NAS. So this is especially for like long-term data storage, whatever. All right. Then you also have, and this, I can actually remove it. Okay, what's that button? That's stupid. Unplug it. Sorry, I'm just unplugging a hard drive, and I'm going to wait till it stops spinning. In any case, you might have seen these types of things, right? So this is, these are both mechanical hard drives, okay? This one, actually here you can see a little bit, like that's the motor there. This sort of section here, you can see that's where the disks are. These two places are where the head, actually this is where the head motor is, okay? Yeah. YouTube it. Somebody opening up a hard drive. You can actually see it spinning and stuff like that. Maybe I'll find one and show it to you guys or something. But, all right. Now, in addition to, so this is a bigger hard drive. I mean, physically bigger. You might have an expansion drive or something like that. If you have a spinning hard drive in your laptop, it's going to be this size, not this size, because that's too big to go inside of a laptop. If you open up one of these things, it looks like this. Okay, so this is also a spinning disk hard drive. Okay, but it's physically smaller. And I think this one is like 500 gigabytes. Okay, so each of these are spinning disk hard drives, and they're for long-term storage. Now, the ones and zeros that the files are on each of these, the disks are magnetic. In fact, if you have a broken hard drive, take it up, pull it apart and stuff like that. And then there's some really strong magnets in here. If you like strong magnets, I don't know, I like them for things, put stuff on the fridge and what have you. Yeah, you get some free magnets here. Why are there magnets in here? Because the disks are magnetic. And the head does not touch the disks, right? If you played records a lot, or if you've heard about them, the more you play a record, because the needle actually touches the disc, it will like wear down over time. So if you listen to a record over and over and over and over and over, after some time, the sound quality will be reduced because of the friction again and again and again of the needle dragging across the disc. You don't want that in a hard drive. So instead, they use magnetic disks, and the head reads, it doesn't have to touch, but it can tell if this part of the disk is positive or negative. Rather, the pole, is it north or south, right? So north pole means 1, south pole means 0. Okay, and when you're writing to the disk, it's like, applying a magnet. It flips, all of these different poles. And that's how the file is stored on a hard disk. Okay, so for a hard disk, it's sort of magnetic and whatever. Okay. Right, so this is long-term storage. And the way that it's long-term storage, like this is not plugged in, right? But if I plug it in, all the information that was there is still there. Also, it's another reason why you never want to get a magnet near a hard drive, or near a spinning disk hard drive anyway. Probably not near other ones as well, but particularly bad for these. If you ever want to get rid of something incriminating, take a really strong magnet to it, and that will scramble the information. I think there was a scene in Fight Club about that, but it was for VHS tapes. Whatever. Okay. Now, your phone, for example, does not have this type of disk. 1, because it's too big. 2, because you don't want something that's spinning and like moving around all the time. You pick up your phone, put it in your pocket, put it on the table. You're doing lots of stuff with your phone. So they don't use these kinds of drives. They use something like this. This is one kind. This is a solid state drive. Okay. This one is 240 megabytes, but whatever. It looks like this. Okay. There's different kinds. There's ones that look a little different from this. This is one of the 2 major kinds. I have another one, but I don't want to take it out of my computer. Now, this is much faster than this type of hard drive, okay? Because here, you have to wait for the thing to start spinning, you have to wait for, it's mechanical, right? So it takes longer to retrieve information. Where this, things are stored on here is it, these chips, okay? And so this isn't magnetic. Instead, this is electrical. Okay, so yeah, whatever. I'm not an engineer, but I know a little bit. Okay. So, and this, therefore, this is much faster. If you might have this in your laptop, I don't know, could be. But like if you have a home computer or something, one of the best things you can do is to move your operating system, if your Windows, Linux, Mac, whatever, if you move it away from the mechanical drive and you put it on a solid state drive, your computer is going to boot much faster. Any programs that you put on here are also going to start faster. Now, for other things like music, movies, stuff like that, it doesn't matter if you're waiting like another second or something for it to start. So you don't really need a big one, but definitely your operating system you should put on here. Big files, games, yeah, music, movies, whatever, put them on these. Okay, so that's a solid state drive. You also have this, which is a micro SD card. This you probably have seen before. I'll show you the other side. Whatever. They're small. This is not as fast as this because it's smaller, and that's basically the benefit of this, is that it's small. This one is 128 gigabytes, whatever. Okay, this is also long-term storage. You know, you'll put these in cameras, or, you know, your phone, if you're lucky enough to have expandable storage, would be using this micro SD kind of. Let me see if I can get the, yeah, focus there. Yeah, whatever, micro SD. Okay, so each of these, you know, these 4 things are long-term storage. Separate from that, you have RAM, random access memory. That looks like this. You've never seen it before. This is, I believe, oh yeah, that's a 4 gigabyte stick. So you usually have, I mean, you could have 1, you could have 2, 3, 4. Some computers can hold up to 8 of these sticks. But this is RAM, and it's kind of similar to an SSD in that everything is stored with like electricity, basically. The difference is, well, one, this is much faster than even a solid state disk. RAM is very, very fast. So when you can, move things onto RAM. We'll talk a little bit more about this when you're, actually that's where the data, these data structures are going to be loaded from. They're going to be moved from a hard drive into RAM. And once they're in RAM, you know, they're great. But you only have one type of data structure here, and most of your data is on this kind of drive. Why not put everything here? Well, there's a couple of problems. When you lose power, everything in this goes away. It's lost. Unless like you deep freeze it and like, I don't know, that's another thing. Right, so if you've ever been like working on a paper or something, you know, like typing it up in, I don't know, Word or whatever, and then your computer all of a sudden loses power and you didn't save, and you boot up your computer again and it's gone, that's because it was being stored in RAM. And so it's good to have it in RAM. That's where you do want it. But if you suddenly lose power on your computer, then this gets wiped out. I mean, this needs a constant supply of power in order to work. So we'll be talking a little bit more about RAM. The main thing to know about this is that it's very fast, but it's temporary. Okay? When you can, it's helpful to put things on memory when you're able to. But it's only going to be for short-term storage, not long-term storage. Long-term storage, you got, you know, your SD cards, your SSDs, but more likely than not, it's not going to be this, because that's, you know, you don't need it to be small. It'll be on drives that are like this big. Okay. In fact, on many hard drives, on many database systems, they will have many of these. Like if you opened up the computer box, then you would see, I don't know, 8, 10, 20 of these. because I mean that's what its main thing is it's supposed to be storing data. Another reason why these are still being used and probably aren't going anywhere is because they're cheaper. First of all, I don't even think that they manufacture 8 terabyte. No, they probably, I don't know. Yeah, an 8 terabyte SSD? I don't think so. Usually these are like, this one's 256 gigabytes. So this one can hold like 256 movies. Okay, that's like how big this is. Maybe you can find them in like 512 gigabyte or like a 1 terabyte, maybe 2 terabyte. I know that they do have 1 terabyte, but 8 terabytes, I don't think so. Just because it's expensive to manufacture. And so that's why these are used, because they're cheaper. Okay, so that's another, this is another thing to know, I guess, about file sizes, is that, you know, there's the number of ones and zeros, and there's that perspective on it, right? I mean, if it's 1 megabyte, a gigabyte, whatever. But another thing to know is like how much actual like disk space does that use, right? Depending on the amount of data that you're working with, how big of a drive do you need? And probably you're also going to want backups. At least one. So, you know, whatever size your data is, you'll probably be doubling that amount for important things. And yeah, so having a concept of, you know, how much it costs, both in terms of the number of hard drives and then also the money it costs. Like how much does it cost to store a terabyte of information? Depends. You know, it depends on how you're storing it. If you're storing it on something like this or something like this, but okay. So let me pause. I don't know how many of you I don't know, maybe you guys know all this stuff, or you've seen all these things, but I think it's good to go over anyhow. None of this is going to be on like a homework or anything, but this part will come back, and I will ask questions about it. We'll come back to it more later, but yeah, because that's important about like why we use B+ trees and things. Okay, let me pause. Any questions? How much storage does each type of drive usually have? Out of curiosity, will SSD ever be cheaper than HDD? By the way, that's a hard drive disk. SSD is a solid state drive. Let's see. I don't think that SSD will ever be cheaper than a hard drive. Yeah, I don't think so. How much storage does each usually have? It changes. I would say for these types of disks, like, I don't know, I have some really old ones that are like 512 megabytes. Like on a big disk like this, you know, 512 megabytes, it's like nothing by today's standards. But I would say for these kinds of drives, maybe 1 terabyte-ish is standard. I mean, around that, you know, so maybe 500 gigabytes, maybe 2 terabytes, 3 terabytes, 8 terabytes, 10 terabytes is getting up there. Yeah, that's not as common for like most consumers, like for most, you know, people. But I don't know, if you play a lot of games or if you watch a lot of movies or whatever, if you have a lot of data, like I'm running like machine learning models and stuff like that generate a lot of data. So this is on the bigger end of it. Yeah. Let's see. For these types of drives, again, probably around a terabyte-ish. These probably don't go much into the like 8 terabyte kind of territory, just because they're smaller. SSDs, again, these are like 256 megabytes, I'm sorry, gigabytes, 256 gigabytes, 512 gigabytes. Those are probably the most standard. You can get them in like 1 terabyte. I've seen that. RAM, it depends. This is 4 gigabytes. That's a decent, this is about the bare minimum that you'd want. You could have, 4 sticks of 1 gigabyte each, but for modern day things, 4 gigabytes of RAM is sort of the minimum. 8 gigabytes of RAM is better. You can get up there though. I mean, I think in the computer that I use for work, it's 32 gigabytes of RAM. I think I have 40 gigabytes. Yeah. But that's not like normal to have. I'd say between 4 and 12 gigabytes, maybe 16 if you want to. 16 is on the upper end. That's for like maybe gamers and stuff. All right. What should your main takeaway from the discs part of the lecture be? Your own education, I guess. I mean, I'm not going to ask you questions about it. It's more of, again, foundations, right? Like, what are we talking about? Where, like, we're talking with databases, I think it matters that people have, or that students in my course have a concept for these kinds of things. These aren't magic. Maybe, I don't know, yeah, people might not have seen these kinds of things before, and now you know. Hopefully it will help put other things more into context. I'd say the biggest, maybe the takeaway is that databases are stored on spinning disk drives, and spinning disk drives have on the screen here tracks, sectors, and blocks. Especially the blocks we'll be coming back to. And part of this is relevant for the next thing that I want to bring up. But, okay. All right. Anything else? No. Okay. Now, I'm going to say something that might sound a little bit like a contradiction, but it's not. And I would like if you guys, or if there's anybody who has an idea about how to solve this problem. Okay. Here, going back to arrays versus trees, we should have a preference for trees because you can insert and delete faster. Arrays have this problem when, like this, where, if you want to add a number, in the worst case, this can take time n. Again, that's because the worst thing that can happen is if you need to insert something at the beginning of the list, and then you have to create an empty array, or an empty cell at the array. Oh, now I can actually say a little bit more about this. Why can't you add a space anywhere you want? Why is it always at the end? Why can't it be at the beginning, etc.? The reason is for some legacy reasons, like when they were first starting computers, and now I'm still getting to the point a little bit. The way to think about how things are stored on a hard drive, in memory, all of it, you should think of it as an array. Okay? So with that, the way that operating systems work is if you start a program, the program will ask the operating system for a range of memory. Maybe this is, I don't know, 5 megabytes, right? That's how much room the program is asking for. But the program isn't going to use all of the 5 megabytes. Maybe the program is just using 1 megabyte. But now it has room to grow, okay? So the array here would be stored, somewhere in this green section. And then when you need more space, you have room to grow, and that's at the end. Okay, so this is why arrays, you can't put it at the beginning, because that's not where your program is physically located in memory. Your program is physically blocked. It's not allowed to go outside of this region by the operating system, but it can work within the range that it's been given. And so everything will be at the front, and then when things grow, it will grow this way. Okay. So back to this. Inserting something here is the worst case is when it needs to go at the beginning, because everything needs to shift over so that you can have the empty space at the beginning to put your element, okay? That's why insertion takes time n. Okay. Also, with these, this is the way that a disk looks. Like if you opened one up and you looked under like a microscope, I don't know if you could see with your naked eye. In any case, logically, there's tracks and sectors, and the intersection of the two are blocks. Okay? Now, when I say that the right way to think about hard drives or about storage space is as an array, that's because, let's look at one of these blocks, right? I'll take this block here. So this is going to be a physical strip on the disk, right? The red thing here. Well, maybe I'll do it like this. So that's the block. I mean, it's a physical strip on the disk itself. A strip of what? Of 512 positions that can each have, North Pole, South Pole, North Pole, whatever, and you have 512 of them. Okay, and that's the length of this thing. And that's how data is stored on the hard disk, be it RAM, SSD. I mean, it might not be North Pole, South Pole, but physically, there's arrays like this, okay? And so this is why this is the correct way to think about it, because it's the truth. This is the way it's actually stored. So whenever anybody's talking about memory or hard drive space, they'll always describe it in terms of an array. Now, because of this, how we like trees, again, because they do insertion and deletion very fast. How can we have both? Physically, things are arrays. It's not just the way to think about it, it's almost literally what they are. So, how can we how can we have both? Like, we like trees. How can we use trees if we're stuck with arrays? I'll give you a minute to think about it if you like, but I would like to hear some thoughts. It can be done, I'll tell you that. Could we fill in the array in the order that we would fill in the tree? By establishing some sort of conditionality. I'm not sure what that means, a type of conditionality. The other one, could store the array in the order you would fill it in a tree. That's pretty close to one way of doing it. There's two ways that I can think of, but print the array like you'd read a tree from the root to the children. That's also pretty close. Okay, I'll talk about two ways, and I'll start with the one that people, a couple people have gotten really close to. So, here. The goal. Print in order of high to low from the left side. You mean like this, but just in reverse order? Does the tree have to be full and balanced? No. But you can assume that they, well, not necessarily. A balanced tree is balanced. A binary tree or a binary search tree is not necessarily balanced. Okay. So the goal. To store a tree in an array. And instead of store, I'm actually going to use another word, encode. Okay? So we're going to take a tree and we're going to encode the tree in the array. What would that look like? Let me get one of these here. I'll take this tree, just because. Okay. There we go. Okay. So here's our tree. And so there's two ways of doing this. One which is on the face, simpler, another one which is actually used. I'll start with the simpler one, which is what people were getting very close to. So, I'll call this layer by layer encoding. So what you do, 8. Okay. What you do is it just what the words are. You do it layer by layer. So here, layer 0, that means you're going to put 10 at the beginning. And then you encode the next layer, 5 and 20. Then you encode the next layer. Four, 7, 15, 30, and now the last layer. Isn't there a formula that relates a parent to a child in an array? Yeah, right, exactly. It's something like this, 2k plus 1. So here, the left child is going to be, let's see, of node I, is going to be at 2i plus 1, and the right child is at 2i plus 2. All right, so for the 0th node, its left child is at 1, position 1. Its right child is at position 2. How about the number 5? Its left child is at position 3, so 2 times the number plus 1, and its right child is at 2 times that index plus 2. Left child of, so actually, sorry, instead of node I, I'll say of node at index I. Okay. As another thing, that's a detail, but yeah, it's good to know, sure, if you want. and that is the way that you would traverse the tree. Actually, yeah, we'll do that real quick. But before that, I'm gonna have to move over here a little bit because now we're missing the number 1. Number 1. Now, one of the things about the layer method is that because it's layer by layer and that you are using this method of traversing the tree, you need to use up all the space. So here, if the tree is not balanced, then this is bad for the layer method. So here, this would actually be 1 and then null, because there's nothing here, there's nothing here, nothing here, nothing here, nothing here, nothing here, nothing here. So you need 7 nulls. I'll just write n. 2, 3, 4, 5, 6, 7. Now this tree is encoded, and you have to have the nulls. It's not optional. In the layer method, you have to have them. Again, so let's see why. I think. I'd have to do an unbalanced tree. I want to get through this. So, okay. So using these, okay, let's find the number 15. Okay, that's the one that we want to find. And how would this work on a binary search? Start at the root, go right, and then go left. Okay, so easy enough in the picture. How would that work in the array? Well, you start at the root. Oh, come on. Which is at the beginning of the array. Okay, and we're looking for the number 15. 15 is bigger than 10, so we should go to its right child. That is at 2 times 0 plus 2, position 2. So then we jump to here. And now 15 is smaller than 20, so we want to go to its left child. We are at index 2, so index 2's left child is at 2 times that index plus 1. So 2 times 2 plus 1 is 5. And so then we go to index 5. And that's it. Okay? Okay, yeah, so this is one way of doing it. And, sorry, now we have the best of both worlds, right? We can use an array, not because necessarily we want to, but because we have to. Like, that's just the way that hardware that we have works. But you can encode the tree. What encoding means is that you interpret the sequence of numbers in a particular way. So here, the problem up here wasn't anything inherently wrong with the array that was giving us this insertion time, right? There's nothing, because there's nothing inherently wrong with it. The problem with this way of doing it is ordering things from big to small, or from small to big, right? And then trying to maintain that order, like that. That's the problem, is that this isn't the right way to order the numbers. A better way to order the numbers is like this: 10, 5, 20, 4, 7. It's not from smallest to biggest. but it's a tree. I mean, it's an array, but I mean, like, these numbers, you interpret them as a tree. You can traverse the tree in this way. All right, so you start at the root, you go left child, right, right child, whatever it is, until you end. Okay? Now, the problem with this, this is fine, but it can waste space, especially if you have an unbalanced tree. Think about how that would work. Let's go to our unbalanced tree here. Where is it? This one, right? Try to put that in an array. You can, but boy, is it a lot of wasted space. I mean, so how would that look? You'd put 10 at the beginning, okay? Then its left child is 4, then its right child is 12. But now there's missing places here. So it'd be null, 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 and now the number 13, right? Now for the next layer, these are all missing, right? So you'd have that many nulls and then the number 14. And then for the next layer, you'd have a bunch more nulls, right? For the missing places. And you have to have the nulls there, because that's the way that you traverse the tree. It's by index number, multiplying it by 2 plus 1 or plus 2, depending on if you're going left or right. So if you were to encode an unbalanced tree, that's a lot of nulls. It's a lot of wasted space. Okay, so this is method 1. And now I'll talk about method 2. The pointer method. Okay, so the way that the pointer method works is that each node is going to take 3 indices, okay? So each node encode each node as, so we're going to be taking up 3 positions now. That's going to be the node value, and then the left child pointer, and the right, oops, sorry about that, child pointer. Okay? So I'll encode the same tree, and I'm going to do it a little bit out of order, just to make a point. I don't know how many places I'll need, but okay. So the first 3 locations, I'll put node 30. So there's the value of the node, and it does not have a left or a right child. So these would be null, or whatever throwaway value you want. I'm just using null. Okay, so that's one node, right? And now for another node, how about 20? So that's the value of the node. And remember, each node is going to take up 3 blocks. And here would be value, oh, I'm sorry, that we don't know yet. Its right child is going to be at position 0. So the 0 here, that's what a pointer is. It's a pointer to the location of the index. And now I'll do node 15, just to round that out. And node 15 doesn't have any children, null, null. And 15 is at position 6. Again, the 6 is a pointer to the index of the starting point of that node. Okay. I don't know. If we do node 1, that'll be null, null. 4, why not? Then its pointer left is at position 9 and null. So it doesn't have any right children. This is one node. This is one node. This is one node. It's one node. Okay. I'm not going to finish it, but I'll leave that to you as an exercise to, finish what this would look like. I will ask this type of question on homeworks and exams. Take this tree and encode it in an array. I might, if I don't specify, do it layer by layer or the pointer method. You can do it whatever way you like, unless I specify otherwise. Let's see. And I'm drawing these arrows and stuff just to kind of, I don't know. You can write the numbers of the indices, or you could also just give the arrows. That's fine. That's what a pointer is, but 6, 9. Okay. So the benefit, so there's a couple things. One thing is the order of each node here doesn't matter. Okay, that's one benefit of this method. Because you can use pointers and you can jump all around. So you don't have to put 10 at the beginning and then 5 and then 20. You don't need to order things like that. You do need a pointer to whatever where the root of the tree is. But if you have a pointer to the root, you know where the root is, you know where to start, then it's easy enough to traverse. The other good thing about this is that even in an unbalanced tree, this is very memory efficient for any kinds of trees. And so the second pointer method is the way that's more common. That's more actually used. Okay, so that's it. Yeah, I'll hang out if there's any questions.